So, we hear a lot about the search for magnetic. According to what we read, it's theoretically possible.
Well, you see, the problem of the magnetic monopole, this one. Divergence of B is equal to 0. So according to Maxwell's theory, there cannot be a monopole. But is Maxwell's theory correct?
We have shown that B is a theory of the electric potential.
We have, you see, we have made experiments, we have made measurements in regions of space which doesn't have a monopole. We haven't measured them in a monopole yet. So within our measurements, the divergence of B is 0. But did we do enough measurements to say that magnetic monopole doesn't exist anywhere in the universe? Well, you see, for example, if you don't have any charge, if you have a region which doesn't have any charge, then the divergence of the electric field is equal to 0. Which tells me that we can write the electric field as the curl of some vector field. Well, is the divergence of electric field is 0? No, if there are electric charges. Well, divergence of B will not be 0 if there are magnetic charges. But since we haven't been able to measure any magnetic charge yet, then all we could measure up to this point is that the divergence of B is 0. That is our measurement. Now, is it the fundamental theory? We don't know. That is, if someday we can find some magnetic monopole, in that case we will see that we will prove that the divergence of B is non-zero. Now, of course, the question is, okay, why are we looking for magnetic monopoles? What's so interesting about them? So that would, I mean, if nothing would be interesting about some magnetic monopole, then we would just say, okay, if we find it one day, fine. But it can answer an important question for us. And that is, why is the charge quantized? You see, we have this, let's just call the electron has charge -1, let's say. The proton has charge +1, and the proton is made up of quarks whose charge is 1/3, -1/3, or 2/3, or -2/3 the proton charge. So if you just call the 1/3 the proton charge as your electric charge quantum, all the charges we have measured is an integer multiple of that quantum. But why? Our current theory doesn't tell us that it should be so. In fact, according to our current theory, the standard model, well, the electric charge of particles can have any value. It doesn't have to be an integer multiple of some quantum. But if there is a monopole, it would tell us that the charge of this magnetic monopole multiplied by the electric charge has to be some integer multiple of some basic quantity. So that would tell us that the electric field has to be quantized. Electric charge has to be quantized. And it's enough that there is a single magnetic monopole in the universe for us to say that, okay, the electric charge has to be quantized. So that's why for us it is important. If we can find a magnetic monopole, that would tell us that why the electric charge is quantized. And it will also, of course, tell us that our Maxwell's equations are not complete. We have to complete it with magnetic charges. And in fact, I mean, you see, we have this theory that we call the standard model. If you make any modifications to the standard model, these new theories predict the existence of magnetic monopoles. They modify these Maxwell's equations, let's say. And the magnetic monopoles should exist. And of course, then the question is, if they should exist, if we have a theory which contains some magnetic monopole so that they explain why the electric charge is quantized, then why don't we measure these magnetic monopoles? So those are some of the things that we are trying to understand. Why can't we create any magnetic monopole? We have been doing all these experiments at very high energies. So why can't we detect them? We don't know. We are looking for answers. Well, the lectures are most of the time about what we already know. The research is about what we don't know. Okay, so let's look at the force acting on magnetic dipoles. Magnetic dipoles. Well, what is the force acting on an arbitrary current density? Well, you see, you remember the Lorentz force, which was Q E cross V, E plus V cross B over C. This is if E is equal to, let's say, this is QE, this is the electric force, and the magnetic force is QV cross B over C. Well, you see, Q times V is nothing but the current density. So the force acting on a current density is 1 over C, J at the point R multiplied with B at the point R, dV. Or this is, in fact, the same thing as 1 over C, I times dl cross B. Well, if E is, this is the magnetic part. So we will be interested, we are mainly interested in systems that are neutral. So as a whole, there's not an electric force acting on them. There are no electric fields. So, okay, let me put the R prime over here. So we will again assume that the current density is kind of localized. It is this, our system is at the point R. Our system has some size D, and D is much smaller than R. So we can expand this B, R prime. Let's say, let me just write this, take any vector in our region, or let me write it in this form. This is equal to B, R plus R prime minus R. Now this R prime minus R is small, that's what I will be assuming. So we can basically make a Taylor expansion in that. So that will be my strategy. So what I will do is, this is the general force expression. If you have any system of currents, you put it in a magnetic induction field, in a B field, it will feel some force. And the total force that it will feel will be given by this integral. Now my strategy will be, I'm assuming the magnetic dipoles to be small. Small compared to the variations of the magnetic field, because you cannot really say that something is small. It has to be small compared to something. In our case, it will be the variations of B. So we will assume that B is almost uniform over our magnetic dipole. In the volume of our magnetic dipole, we can add the corrections. So I will be expanding B around the position of my dipole. And I know that my dipole is localized, so this R prime integral is over a very small region. And then I will take this B, or its derivatives at the point R out of my integral, and I will try to convert what remains into our definition of the magnetic dipole moment. Okay? Well, this is equal to B at the point R plus R prime minus R, that the del operator acting on B at the point R. Plus other terms. Do you agree with this expansion? Well, for simplicity of notation, R is equal to 0. I will just choose my origin to be at the center of the dipole. I don't want to write R prime minus R all the time. So B at a given point R will be B R prime B0 plus R prime dot the del operator acting on B0. Now again, just a note on this notation, this del operator acting on B0 is not, I just put the position 0 and then take the derivative, that is 0. I first take the derivative and then put 0 in the place of the derivative. So this is equal to BI, the I component is BI0, which is some constant, plus xj prime del over del xj b I evaluated that xj is equal to 0. In terms of the components. Now, this is not a vector. Which one? Why? It's not the divergence. You see, the divergence is if I take the derivative of the j component of b with respect to xj. You see, this is the derivative of the I component of b with respect to xj. This is 0. Del bj over del xj, this is equal to 0. In fact, derivative of bi with respect to xj is equal to minus the derivative of bj with respect to xi, since curl of b is equal to 0. But hold on, curl of b, is it 0? It wasn't 0. But you see what we are actually studying here. We have these currents over here. We put this in a magnetic field. What creates this external magnetic field? Some charges over here, not inside our dipole. So curl of B in the region of my dipole, magnetic dipole, is 0. Because curl of B in general is proportional to the current, which creates this magnetic induction. But I have this current over here. Other currents are creating this B field. So this B field created by other fields are non-zero only at the position of the other currents, which is not my J. In this volume, in the volume of my magnetic, in the volume that I'm studying, the curl of B is 0. And since the curl of B is 0, if you, let's say, take the y component, take its derivative with respect to x, minus the x component derivative with respect to y, this is the z component of the curl, which is 0. You see, this curl of B, the z component, this is nothing but by by del x minus bx by del y. This is equal to 0, which tells me that del by by del x should be equal to del bx by del y. So here there's no minus sign, it is plus. So if I take the I component, take its derivative with respect to xj, it is the same thing as taking the j component and taking its derivative with respect to xi. This is one thing I will be using. So, any questions? Now let's proceed. Let's calculate okay, we said that F was equal to 1 over C J R prime cross B R prime time integrated over the volume of my currents. This is equal to 1 over C J R prime cross, well, B R prime is B of 0 plus, no, let me just do it. Look at the components of F. Fi, the I component of F is equal to 1 over C times epsilon I j k, the J component of the current, let me put J prime. J prime just meaning that I'm evaluating J at the point R prime, times B of K, the K component of B is BK0 plus XK prime del XL prime del over del XL of BL0. Plus other terms. Yeah, I'm not writing it as a derivative with respect to XL prime, because basically that derivative is a constant. It doesn't really depend on the coordinate XR prime. I'm expanding B R prime at R prime around R prime is equal to 0. The expansion coefficients are independent of R prime. Sorry, this is not L, this is K. Which is equal to 1 over C epsilon I j k epsilon I j k, I can just take it out. Well, BK0, I can take it out. What remains is J, the J component of the current integrated over the volume, plus 1 over C epsilon I j k, derivative with respect to XL of BK evaluated at 0, and then the integral of XL prime times JJ prime dV prime, plus other terms which I just omit. Do you agree up to this point? I just expanded B around the origin, which is some point inside my magnetic dipole moment. And this is the force, the I component of the force. I will be trying to somehow relate this to my magnetic dipole moment. And, well, it kind of already resembles the magnetic dipole moment. Remember, the magnetic dipole moment was equal to 1 over C R prime cross J prime. That last term over there just looks like R prime cross J prime. We have to do some more work to bring it exactly to that form, but kind of resembles it. Now let's look at the first term. The first term is the integral of the current density over the volume, which we already said that it is 0. The integral of J dV is 0. So this first term is 0. So the force, I'm left with the last term. Fi is equal to 1 over C epsilon I j k del B k by del XL XL prime JJ prime dV prime. Well, to write this in terms of this magnetic dipole moment, let me just take this term, this expression of the magnetic dipole moment. The I component of this magnetic dipole moment will be equal to 1 over 2. Well, you see, the problem over here is if I would just write this, to convert this to XL time R prime cross J prime, I need an epsilon LJ. which unfortunately I don't have. So I will do another trick. So let me look at the mu I component. 1 over c epsilon I jk integral of xj prime jk prime over the volume. I will multiply both sides by epsilon I Lm. Now why? Because on the right hand side I have an epsilon, I want to get rid of it, so that I will end up having some component of x prime and some component of j prime multiplied. The easiest way to get rid of the epsilons is just multiply it with another epsilon. And use the property that epsilon I jk, epsilon I Lm, this is equal to Kronecker delta jl, Kronecker delta km, minus Kronecker delta jm, Kronecker delta kl. This is what I will be using. So if I do that, I get epsilon I Lm mu I. This is equal to 1 over c Kronecker delta jl, Kronecker delta km, minus Kronecker delta jm, Kronecker delta kl of xj prime, jk prime, dv prime, which is equal to 1 over c the integral of xl prime jm prime, dv prime, minus 1 over c the integral of xm prime jl prime, dv prime. Almost. Now I have two terms. But remember, we had already proven one property of the integrals of j's. We had shown that xi prime jj prime integrated over our volume, this was equal to xj prime ji prime integrated over our volume with a minus sign. So the second term on the right-hand side is, in fact, the first term on the right-hand side. They are the same. So it just tells me that epsilon I Lm mu I, this is equal to 2 over c xl prime jm prime dv prime, or xl prime jm prime dv prime, this is equal to c over 2 epsilon I Lm mu I. So this is another relation relating the integrals involving the coordinate multiplied by the current, various components, to the magnetic dipole moment. Whenever I see such an integral, I can always replace it with the magnetic dipole moment. So let's go back. This is the force I have, the I component of the force. This is equal to 1 over c epsilon I jk, derivative of bk with respect to xl. This derivative is evaluated at x is equal to 0. I'm not writing it explicitly, but just keep that in mind. And here I have the integral of xl prime with the j component of the current. And that just gives me c over 2. Well, let's see, epsilon, let me not use the I, but use the symbol m or n, mu n. L is L, m is j. Well, you see, I is a dummy index. You see, in this term, in this expression, I is a dummy index. I'm just summing over I. Now, in this last expression, I is not a dummy index. I mean, a dummy index just means that you can just change its name at will. But here, in this expression, I have another I, which is not a dummy index. I have to make sure that those two indices are different. One I is Fi. I'm looking at the I component. That's a significant index. The other one over here is the dummy index, which I'm summing over. Those are different things. So that's why, not to confuse these two different symbols, I just name them differently. But you see, in this expression, the second index is the index of xl prime. The third index is the index of j prime. So I have those, in this expression, in this rectangle, L and M are significant indices. So here I have the x prime has the index L, so that is the second index in this epsilon. The j prime has the index j, that is the third index in this epsilon. Okay. Okay, now I have the product of two epsilons again. So this is equal to 1 over 2. And let's see, let me just rewrite them in the form minus 1 over 2, epsilon I k j. I just exchanged the order of j and k. Epsilon n l j mu n times derivative of bk with respect to xl. Now the reason why I exchanged that, I'm always used to having j's at the same position. So just brought the j's. J is a dummy index. I'm summing over j in the product of the epsilons. I just brought them into the same position. That is what I'm familiar with. This is equal to minus 1 over 2 Kronecker delta I n Kronecker delta k l minus Kronecker delta I l Kronecker delta k n and mu n derivative of bk by xl. So let's just multiply them out. This is minus 1 over 2 mu I derivative of bk with respect to xk minus mu k derivative of bk with respect to xi, or minus 1 over 2 mu I. This is the divergence of B. Minus derivative with respect to xi of mu k bk. Well, the divergence of B is always 0. So that leaves me with fi. This is equal to 1 over 2 the gradient of mu dot b, the I component, or fi is equal to 1 over 2. This 1 over 2 I didn't like. It shouldn't be. Gradient of mu dot b. This is the force acting on my dipole. By the way, this we can also write it in a different form. You see, Fi was equal to 1 over 2 times mu k del over del xi of bk. But this is the same thing as 1 over 2 mu k del over del xk of bi, which is the same thing as 1 over 2 mu dot b, mu dot del acting on bi, or f is equal to 1 over 2 mu dot b mu dot del acting on b. They are both the same things. Again, I repeat, that 1 over 2 shouldn't be there. So let's go back where I missed that 2. So what we did, this is the general expression of the force acting on my system. I expanded B around R is equal to 0. So I have this overall C over here. This is the the B at the origin plus the derivative of B at the origin. And then I can take out that the first term is 0. I can take out the derivative at B at the origin out of my integral sign. So this is the expression of the force we have. Then I looked at the expression of our, this is where I forgot it, the mu is, the definition of mu has this factor too. Mu is not just 1 over c, it is 1 over 2c. Remember, r cross dl divided by 2 is the area. So that 2 is in the definition of mu. So here I have 2c, here 2c, 2c, 2c. So here there is no 2. So there is no 2. So this is the force acting on a dipole. Either this expression above, or you can use this expression below, whichever one you like. You see in particular that if B is not uniform, you will have a force acting on this magnetic dipole. I mean, if you imagine a region of space in which the B is getting larger, like in the north and the south poles for these charges moving in this one element belts, you will get a force that is pushing it back, pushing the charges backwards. So we were discussing what this example of the one element belts. We have these charged particles coming from the sun. They will be circling around the magnetic field lines, and their component in the direction of the magnetic field lines will just push them in the direction towards the poles, depending on where they hit. They will either go first to the north or the south pole. But towards the pole, the magnetic field lines, they start converging to the poles. So the B is increasing. In such a region, if you just apply this force law, you will see that these charged objects, you see, they are rotating around the magnetic field lines. Since they are rotating around the magnetic field line, they have a magnetic dipole moment in the direction of the magnetic field lines. So this, and plus the magnetic induction field, B field, is changing, so there's a force acting on them, and this force is in the opposite direction. It will push them back. Now let's look at the torque acting on any current. Acting on a magnetic dipole. You see, the general expression of a torque is just R cross F. R is the point at which it is acting. So if you have a current system, there will be a different force acting at different points. So the torque acting on a system of currents will be just R prime, let's say, cross dF prime. dF prime being the force acting in that region of space. Well, dF prime is nothing but 1 over C J prime cross B prime integrate over the volume, dV prime. This is the torque we have. This term is nothing but our dF. You can think of it as just Q times V, Q times V over C. Q times V is just J. Q times V over C cross B prime, B. It has exactly the same form. And actually that's what we are basically doing. We are just dividing our region of moving charges into very small volumes. Each one of these volumes have a charge q. They are dq. They are moving with a velocity, let's say v prime, and q prime times v prime is nothing but j prime times dv prime. So the torque is 1 over c r prime cross j prime cross b prime dv prime. Well, we will just do the same trick. This will be equal to 1 over c r prime cross j prime cross b at 0 plus r prime dot del acting on b prime at 0 times dv prime which is 1 over c r prime cross j prime cross b0 dv prime plus 1 over c r prime cross j prime cross r prime dot del b prime 0. dv prime plus other terms. Well, for us the first term will be enough to start with to calculate a non-zero torque. This is r prime cross j prime cross b 0. This is just equal to j prime r prime dot b minus b r prime dot j prime. So let's look at the last term. You see, we had already proven this identity xk prime jl prime dv prime. This is equal to minus xl prime jk prime. dv prime. If you multiply both sides by Kronecker delta kl, you get r dot j prime, r prime j prime dv prime is equal to minus r prime dot j prime dv prime. So if something is equal to minus itself, it is 0. We don't get any contribution from this one. Remember, we should put this into this integral over here, integrate this around over r prime. So that term doesn't contribute. So we only have contributions from the first term. So let's see, the torque will be 1 over c times this first term, j prime, times r prime dot b, 0, dv prime, plus other terms. Let's look at the I component of the torque, which will be equal to 1 over c ji prime xk prime bk dv prime this is equal to minus 1 over c bk, or let's say tau I is equal to, let's take the bk out, 1 over c bk xk prime ji prime dv prime. Now I have the product of some component of r prime with some component of j prime and integrated over v prime, but we had already expressed this expression in terms of the magnetic dipole moment. You see, we have this general expression over here for such integrals. I will just put it over there. So tau I is equal to 1 over C Bk times C. I is a dummy index, this I over here, so not to confuse with the index of Ti, I'm again changing its name, so it's epsilon n. You see, L is the index of x in this expression, but now the index of x is k. M in the index of j, but now the index of j is I times mu n, which is equal to, C's cancel, epsilon I and k mu n cross bk. But this is nothing but mu cross b, the I component. So the I component of the torque is equal to the I component of mu cross b, which basically tells me that the torque is equal to mu cross b. So this is valid in general. Now the tricks that we have been mainly using. One is this relationship that we had obtained. Some component of r prime multiply with some component of j prime, integrate over the volume. You can always write this in terms of mu. And in fact, even this expression tells me that if I exchange the position of L and the indices L and M on the left-hand side, well, I'm changing L and M in the epsilon Levi-Civita tensor, but the Levi-Civita tensor under the exchange of L and M changes its sign. So if I have this product, if I change L and M, the product changes sign. That's another thing that I have been using. Just over and over again. Now, the computation, the derivations seems kind of boring. It is boring to watch. And I would suggest you to strongly to go over them. You will see that they are not really complicated. We have many indices just running here and there. It seems complicated at first, but when you actually do it, you will see that it's just some trivial tricks just repeated over and over again. And the final result is, this is the torque, the force is the gradient of mu dot b. Well, actually, these were some of these results we had already derived in your first years for simple systems. But now we have proven that these are true in general for any current system. If you have a localized current, you can always define a magnetic dipole moment for this localized system of currents. And if you put it in an external magnetic field, there will be a force acting on it, a torque acting on it, and the force and the torque acting on this system will have this form. Now on Wednesday, we will just go over to our simple systems, like these loops, and we will see how to derive these systems in such simple cases. And then we will proceed with the magnetic fields in matter. So that will be kind of the end of the magnetostatics. And then I'm hoping to start on Friday on electrodynamics. So there we will have more interesting problems. Now, any questions before you go? Yes. Well, you see, if you look at the catalog of 334,